So let's take a look at the case study and let me show as to how to import the data file that we have chosen for our case study. As I had explained, this is the case study on the Sweden insurance data. This data is in the CSV format, and hence I am going to first of all import the data file in R. This is the R editor wherein I am going to write all the commands that I want to use in order to build the simple linear regression model and hence to meet the objective to predict the value of the claim amount for the given value of the number of claims. In the first place, let me import the data file and store it in an object called as SI. As you are aware, R is the object-oriented language, and hence whatever operations we perform, they get stored in the form of an object. Let us first take a look at importing the data file which is stored on my device and then use it further. This particular command helps me import the data file. So SI is the name of the object wherein I shall store the imported data file. Read.csv command in R with the file.choose as an argument and header equal to true will help me bring this CSV file in the R environment. So let us see how to import this data file in R environment, and let's see how read.csv with file.choose as an argument and header equal to true lets me bring this file in R. Let me run this particular command, and as you see over here, file.choose option allows me to import the file which is stored on my device. So Swedish insurance is the CSV file which I am now importing in R. Having imported this data file, it has gotten stored in the object SI. Now let me check the number of variables and the number of observations that I have in this data file. To do so, I use the function dim, which is dim or dimensions. So dim function enables me to check the number of variables as well as the number of observations in my file, which is Sweden insurance data file stored in an object SI. Let's see what happens when I execute this command. The results are seen in the console, and here we see that the dimensions for this data file are given by two numbers out here, which is 63 and 2. The first number indicates the number of observations that I have in this data file, and the second number, which is 2, indicates the number of variables that I have in this data file. Just to be sure as to whether I have imported the correct file or not, it's a good practice to use the head function. The head function, when I apply to this object SI, and if I run this command, it shows the first 6 rows of my data file SI. So my first variable is claims and the second variable is claim amount. So this is my variable X and this is my variable Y. The objective of this study is to estimate or predict the claim amount for the known number of claims. Now this is a bivariate scenario. So we can see that there are two variables X and Y which seem to be logically correlated. But it's not enough just to use the logically correlated variables, and hence the first step to check or to explore this bivariate relationship further is to check whether graphically we can find out if these two variables are related to each other. As seen in my earlier module, the first step to explore the bivariate relationship is to draw a scatter plot. A scatter plot will enable us to see whether these two variables, claims and claim amount, are showing any relationship. So to draw a scatter plot, a graphical method which is to understand the nature of the relationship the function that we use is a plot function. So just look at the way we use this particular function. So a plot function, inside the open brackets, we specify the two variables for which we want to plot the scatter plot. So claims is one variable and claim amount is another variable, which both belong to my data file SI. So SI dollar claims and SI dollar claim amount, and with the plot function, I shall be able to get a scatter plot, and let's see what is the output. So you will be able to see the output of the scatter plot over here. So I may be able to zoom this thing out, and this will give us a clear idea as to what is the nature of relationship between the variable claims and the claim amount. So here is the scatter plot, and which is clearly giving us an indication that the two variables, claims and the claim amount, are exhibiting a strong positive relationship. So having checked the scatter plot, it's not enough just to know the nature of the relationship. Hence, we have to further try out a mathematical method to check what is the degree of relationship between the two variables under study. So a mathematical method to study the relationship between the two variables, claims and claim amount, will be to obtain the Karl-Pearson's coefficient of correlation. So I am defining an object coef, COEFF, which is I am defining this particular object, which will store the outcome of this particular function, which is COR. So COR function in R enables me to find out the value of the Karl-Pearson's coefficient of correlation. So with COR function, in the arguments, I specify the names of the variables. Let's see what is the output. So when I run this particular function, as you can see in the console, it doesn't display the output. It just indicates that the command has been executed. Had there been any error in this particular command, it would have been shown over here. But it will not show by default the value of the coefficient of correlation. Hence, in order to check the value of the coefficient of correlation, I call the object coef. Now, if I simply run this coef, I will get the value of the Karl-Pearson's coefficient of correlation. So as you can see over here, the value of coefficient of correlation is 0.91287882. This is a very large value. So we have seen that Karl-Pearson's coefficient of correlation lies between -1 and +1. If the value of Karl-Pearson's coefficient of correlation is closer to +1, then it indicates a strong positive relationship between the two variables under study. Since the value of coefficient of correlation is 0.91, which is very close to +1, we can conclude that the two variables, the claims and the claim amount, are strongly correlated. Now, having confirmed a strong positive relationship between the two variables, the next step would be to build a mathematical model using a simple linear regression analysis. So what I'm doing here is I'm defining an object model 1, and I'm using LM function to build a mathematical model for simple linear regression analysis. Now the syntax goes like this: LM function, and inside the brackets I use the arguments wherein I specify the model. Now the syntax goes like this: claim amount, which is on the left hand side of this tilde, is my dependent variable, and claims is my independent variable. So the function LM, when applied on this particular model, gives me a mathematical model of simple linear regression. It's important to also specify the name of the data wherein these two variables belong. As you are aware, my data is SI, which is Sweden insurance data, and these are the two variables in that data set. So to build a mathematical model, I use LM function with this kind of a syntax specifying the mathematical model. Let's see what happens if I run this command. So you must have noticed that the model function, or rather the LM function, has got executed, but we are not able to view the output. So in order to view the output of LM function, we use a function called as summary. So summary model 1 will allow us to see the output of LM function. Let's run this command and see the output. Now, as you can see over here, after using a summary function, this is the output that we see. It's important to note the coefficients out here. Now the coefficients mentioned over here are the intercept and the claims. So this is like A and B. So I'm sure you all remember that the mathematical model for simple linear regression is y is equal to a plus bx. Now these are the values of A and B which are obtained using the method of least squares. So the LM function will do all of this at one go and allow you to not just build the model, but also to check the goodness of the fit of the model, and also the significance of the influence of the independent variable on the dependent variable. Now this is the value of A. So my equation will look like y is equal to 19.9945 plus 3.4138 into claims. Having built or having estimated the parameters, our next step is to see whether this particular regression coefficient is significantly influencing the dependent variable claim amount or not. And to do so, we perform a test of hypothesis. As explained in the earlier module, we test the hypothesis H0 whether B is equal to 0 or not. There is a test statistic, and this is the value of the test statistic, using which we get a p-value. Comparing p-value with the level of significance, we conclude whether this variable claims is significantly influencing the dependent variable claim amount or not. As you can see over here, p-value is very, very small. You reject the hypothesis H0 that the influence of claims on claim amount is insignificant. So when I reject this hypothesis of H0 be equal to 0, I conclude that the variable claims significantly influences the variable claim amount. As a next step, we look at the goodness of fit of the model, which is given by R squared. As you can see on screen, the multiple R squared value is 0.8333. It means that 83.33% of the variation in the claims amount is being explained by the variable claims, which means that the model is quite a good fit. So the next step would be to check the assumptions of simple linear regression model. Having built the simple linear regression model, estimated the parameters of the model, checked the goodness of fit of the model, the next step would be to check the assumptions of simple linear regression model. To verify the assumptions of simple linear regression model, we have to perform certain residual analysis. So to verify the assumption of simple linear regression, which is mostly related to the residuals or the errors in the model, we have to first of all compute the residuals for the model. Just to remind you, residuals are nothing but the difference between the observed value of the dependent variable minus the estimated value of the dependent variable. So the function residuals, when executed on model 1, will help me calculate the residuals for each and every observation in the model. So what we do over here is we append a variable res1 to my original data set Si. so that I will be able to perform the residual analysis and be able to check the assumptions of the normality of the residuals, etc. Let's see what is the outcome of this particular command. So residuals function, when applied to model 1, we get the following results. Now again, you will see that this data is not visible. So if you want to confirm whether this particular variable is being appended to my original variable or not, what we can do is again use head function. So let's see what happens when I say head of SI. You will be able to see here that the variable res1, which is the residuals, is being appended to my original data set SI. Now I'll be in a position to check the assumption of normality of the residuals. So the first graphical method is box and whisker plot, and the second graphical method is QQ plot or quantile plot. Let's see how to draw a QQ plot for the residuals. So the graphical method QQ plot will be performed using a function QQ norm. So QQ norm enables me to draw a QQ plot for the residuals, which are now appended to my dataset SI. When I run this particular command, what I get is a quantile plot. And here is the graph, or here is the quantile plot for the residuals. Let's try to interpret this QQ plot. We can actually see a straight line passing through this QQ plot. But as we know, graphical methods have their limitations. And one such limitation is interpretation of this particular QQ plot. So in order to confirm whether the normality can be assumed for the residuals, we shall have to perform a mathematical method. Let's see how to verify the assumption of normality of residuals using a mathematical method, which is Shapiro-Wilk test. So to test the assumption of normality of the residuals, as I said, the mathematical method is Shapiro-Wilk test. So a Shapiro-Wilk test tests the hypothesis H0 that the residuals are normally distributed against the alternative hypothesis H1 that the residuals are not normally distributed. Now the function Shapiro.test, which is to be performed on, or which is to be applied to the residuals, the syntax goes like this: Shapiro.test to be applied to residual 1. Let's see what is the output of this particular test. I run this function, and this is the output of Shapiro.test. As we know, for every test of hypothesis, there is a test statistic, and using the test statistic, what we get is a p-value. You see over here that p-value is quite high, and it is definitely higher than the level of significance, which is say 0.05. Because p-value is greater than 0.05, the conclusion is not to reject H0. When I say conclusion is not to reject H0, it means that the residuals are normally distributed. So one of the assumptions of the simple linear regression model, that is the errors are normally distributed, is being verified. Residuals are nothing but the predicted errors. Moving on next to the assumption of homoscedasticity of the residuals. Homoscedasticity means that the errors have constant variance. We have seen how to test the assumption for homoscedasticity. So in the earlier module, we saw that there are two mathematical tests which can be helpful in order to test the assumption of homoscedasticity. One was the Breusch-Pagan test, and the other was the White's test. Let's see how to perform the test of significance or the test of hypothesis for testing the assumption of homoscedasticity. Ideally, residuals should not be heteroscedastic. They should exhibit homoscedasticity. So let's check the next assumption of residuals, and that is to check the assumption of homoscedasticity of residuals. To check this assumption, there are two mathematical tests. One is Breusch-Pagan test and the other is White's test. In order to perform Breusch-Pagan test, we require the package car in R. So before we use the function NCV test for checking the assumption of homoscedasticity, you have to install the package car and then call for the library function. So because I have already installed this car package on my machine, I am not going to rerun this particular command, but let's see what is the outcome of this particular function, library car. Now this has initiated the car package, and with the help of which we will be able to perform this non-constant variance test. The Breusch-Pagan test for testing the assumption of homoscedasticity tests the two hypotheses. H0 is the hypothesis that the errors are having constant variance against the alternative hypothesis that errors do not have constant variance. In order to test this pair of hypotheses, we need a test statistic. This test statistic will follow certain probability distribution function which will give us a p-value. We compare p-value with the level of significance and conclude whether to reject H0 or to retain it. Let's use the function NCV test on the model that we have built, and let's see what is the output of this particular command. As you can see the output of the NCV test, it gives us a value of the test statistic which is chi-squared, and the p-value is 0.055869. Since this p-value is greater than 0.05, we decide not to reject H0, and this means that the residuals do have constant variance. Hence the assumption of homoscedasticity of the residuals is met for this case study. Yet another assumption of simple linear regression analysis is the absence of autocorrelation for the residuals. But as it was mentioned in the earlier module, this assumption holds good only for time series data and not for cross-sectional data. This case study has the data which is of cross-sectional type. It's not a time series data, and hence we will not validate the assumption of autocorrelation of the residuals for this case study. Thank you.